Hi everyone, welcome to MedGoto. In this video, we're going to be covering hypoxic cellular injury changes. This is going to be like a continuation of introduction to hypoxia that we did a couple of days ago. Please, if you have yet to subscribe to this channel, don't forget to subscribe, put on the notification bell so that each time we upload a video, you can get notification. Having said that, let's go to cellular changes that we see in hypoxia. Looking at the diagram by the side there, this is a diagram of the cell. This is inside the cell, outside the cell, so intracellular fluid, extracellular fluid. And inside the cell, we have a lot of organelle there. A couple of the organelle that we have, right? We have the our endoplasmic reticulum, and on the endoplasmic reticulum, those red dots, those are going to be our ribosome, right? And here we have our mitochondria, and they're going to be our nucleus, and of course, this is going to be our lysosome. Normally, sodium, right, is majorly located outside the cell, right? Majority of our sodium are outside the cell, whereby potassium is the major cation inside the cell. So for no reason, if sodium goes into the cell or potassium goes outside the cell, right? That's why God put a pump there so that I can put them back to where they're supposed to be, right? So which is, and because it's going against the gradient, you are taking out sodium from inside the cell to outside the cell where you have a lot of sodium, so you're going to need energy. So that's why we have sodium potassium ATPase, because it needs to go against the concentration gradient. So this pump will take out 3 sodium in exchange for 2 potassium. So 3 sodium going out of the cell, 2 potassium will be coming into the cell. We also have another pump here, which is calcium ATPase, right? So every time we have too much of calcium inside the cell, this pump can help us to pump out some of those calcium so that they can bind to albumin outside the cell, because you don't want too much of calcium inside the cell because it can create trouble, which we have to talk about as we go over this video. So in hypoxia, like we said, right, hypoxia is decreased tissue oxygenation, right? So there is decreased tissue oxygenation. As a result of that, we'll not be able to produce we'll not be able to produce ATP from the mitochondria, right? So because of that, the cell is going to shift its metabolism into anaerobic glycolysis. Because they cannot, there's no oxygen to be able to make ATP from the mitochondria. So the cell is going to rely majorly on anaerobic glycolysis. So that means from glucose, right, to pyruvate. Ideally, if it is the case whereby we have enough oxygen, this pyruvate can go into the TCA cycle, right? And we can use it to make further, we can use it to make ATP, right? But as a result of that, because we are doing anaerobic glycolysis and we can't go into the TCA cycle because of the decreased oxidation of the tissue, this pyruvate, they have to get converted to lactate, right? Or lactic acid. So that's why if somebody have hypoxia, one of the things that needs to be elevated inside the blood is going to be the lactic acid, right? And this can decrease the pH inside the cell. And this is going to be very important. And when we're talking about necrosis, particularly coagulative necrosis, right? So as a result of that, because of decreased tissue oxygenation, right? And then we're only relying on anaerobic glycolysis, so this will lead to decrease in ATP production, right? Because from anaerobic glycolysis, we're only producing 2 net ATP, right? Which is not enough, right? So this will lead to decreased ATP production, right? And because of the decreased ATP production, right, this will affect our sodium-potassium ATPase pump, right? So let's divide the hypoxic cellular injury changes to 2, right? So we have what we call reversible changes. So there are some changes that are reversible, and there are some changes that are Irreversible. So let's start with the irreversible changes. So decreased ATP, right? That means our sodium potassium ATPase pump will stop working, right? So that will lead to impairments of the sodium potassium ATPase. Right? Because remember, when you see the word ATPase, it means that pump uses ATP, right? So if there's no ATP, that pump is going to stop working. Can somebody tell us a drug that normally inhibits this pump, right? Especially in the cardiac system? Very good, right? Cardiac glycoside, right? Example like digoxin, right? So digoxin can inhibit this pump. There's something for us to remember. Digoxin. So because this pump stopped working, so that means sodium cannot leave the cell anymore. So sodium will to stay inside the cell, and anywhere sodium stays, what follows sodium? Water will follow sodium. So when you look at the cell, right, sodium will to accumulate inside the cell because it can't live along with water, right? So as a result of that, the cell is going to swell up. So the first change we have to see cellular swelling, right? And it's not only the cell that swell, all the organelle inside it, they are also going to what? They are also going to swell. So this cellular swelling is usually the earliest changes, right, that we see in hypoxia. So that could be a test question. So the earliest changes that you want to see in hypoxic cellular injury is always cellular swelling, right? So because of the swelling, so the organelle are also going to swell. So we also expect the rough endoplasmic reticulum to swell, right? So rough endoplasmic reticulum swelling. And then because of the swelling of the rough endoplasmic reticulum, this ribosome on top of it, they want to detach, right? So this will lead to ribosomal detachment, right? And then because of those ribosomal detachment, right, that will lead to decrease protein synthesis. And then can somebody remind us what type of protein we normally produce from the ribosome on the that are bound to the rough endoplasmic reticulum? Very good. Those proteins that we need to export out of the body, right? So those secretory protein, right? So they have to be decreased production of them, right? The next one that we're going to also notice, right, as the cell continues to swell, we're going to notice that the membrane is going to be blebbing out, right? Because now the water is looking for where to pass through, right? So that will lead to plasma membrane blebbing. So that's what we can also see. Plasma membrane blebbing. And also the last thing we're going to see, so because of the nucleus also going to swell up, so that will make the chromatin, right, to clump together. So we want to see clumping of the chromatin. So going to be the last, the next changes. So nuclear swelling, and this will lead to chromatin. So don't forget, so reversible changes, cellular swelling, rough endoplasmic reticulum swelling, which lead to ribosomal detachment, decreased protein synthesis, plasma membrane blebbing, and a nuclear swelling, which leads to chromatin clumping. And if you give this patient oxygen, they start making ATP, the sodium potassium ATPase will start working, and that will pump out the sodium and the water. That's why all these changes they are reversible. So let's move on to the irreversible changes, right? So when the decreased ATP is so severe, the calcium ATPase will stop working. So if the calcium ATPase stop working, right? So impairment of the calcium ATPase, right? This is when the problem starts, right? So this will definitely lead to a lot of calcium inside the cell. So there has to be increased intracellular calcium. And then because of the increased intracellular calcium, right, that will start activating enzymes inside the cell. It's just like what we see in if somebody has very high hypercalcemia, and it's causing acute pancreatitis, right? Because those elevated calcium can activate those protease enzymes inside the pancreas, and the pancreas can start digesting itself. Similar process. That's why high calcium is not good for the body, right? So because of this elevated calcium in the cell, they will start to activate those enzymes inside the cell, right? And then one of the enzymes is going to be phospholipase, right? So from the word phospholipase, that means it can break down phospholipids, right? That are present on the cell membrane, right? So as a result of activation of this phospholipase, right, it's going to break down the plasma membrane, right? So the phospholipid in the cell membrane, and that will lead to plasma membrane permeability. Plasma membrane breakdown, and that will lead to cell permeability. And then depending on where this cell is, right? So if this is a cardiac muscle, right, whereby the cell membrane is permeable, right? So all those troponin inside the cardiac muscle, they have to be, and they'll start going to the blood sufficient to have elevated troponin. If this is in the liver, right, all those AST, ALT, the transaminase enzyme, they will also get escaping to the blood. They will be elevated inside the blood. So that's how we know that the liver is dying, right? Um, and then not only the plasma membrane, the cell membrane that will be affected, it can also affect the lysosome too. So the lysosome membrane can also be affected. Right? And as a result of that, what do you normally have inside the lysosome? Hydrolytic enzyme. So that means the hydrolytic enzyme, right? Because if you damage the lysosome membrane, right, they become permeable to rupture, right? And the hydrolytic enzyme now will be released. Right? And then because of the hydrolytic enzyme, they are released now, right? They have to start digesting the cell. And that auto-digestion is what we call autolysis, right? So they will start digesting themselves, right? So that's also another changes that we can see as a result of this activation of this enzyme. This next enzyme that is also going to be activated by the calcium is going to be the endonuclease, right? And from the word endonuclease, we kind of have an idea of what this enzyme is going to do. So this enzyme is going to break down the nucleus, right? So they're going to lead to nuclear degradation. And then as a result of that nuclear degradation, so what are the changes that we're going to be seeing in the nucleus, right? They can have nuclear condensation. They can have nuclear fragmentation. And there could also be nuclear dissolution. And you're going to see all this being called some fancy name, right? So nuclear condensation, which we normally refer to as pycnosis. Nuclear fragmentation, right? Karyolysis, right? And then nuclear dissolution, karyolysis. And the last organelle that could also be affected, right, is going to be the mitochondria, right? So we can also have mitochondria permeability. And then inside the mitochondria, there is a particular protein that's inside the mitochondria, right? And that protein is called cytochrome C. So we call it cytochrome C. This cytochrome C is present inside the mitochondria. We don't want it to come out of the mitochondria because anytime that cytochrome C leaves the mitochondria and come into the cytosol, this cytochrome C can activate caspases, and that can lead to apoptosis, which we want to talk about in the next lecture, right? So because of the mitochondrial permeability, right? So the cytochrome C now, cytochrome C, right? We enter the cytosol, and that will lead to activation of what we call caspases, right? And these caspases, they're also cytosolic protein, and that can lead to apoptosis, which we'll also talk about in our next lecture, right? And of course, with the permeability of this mitochondria, right, all those hydrogen ion, the electron that we normally use to make ATP, because in the electron transport chain, we generate hydrogens ion, right, that allow us to be able to make ATP, right? So because of the permeability now, we're going to be losing those hydrogen, right, from the mitochondria, right? All those electrons will be lost, and then we cannot generate ATP anymore because we've lost those down gradients, right? And that can also further lead to decrease in what? Decrease in ATP production. Okay? So in summary, right? So in summary, hypoxic cellular injury, right? We divided them into the changes we divided them into two: reversible, irreversible. So if there's no ATP, sodium potassium ATPase pump is going to stop working, and as a result of that, the sodium cannot leave the cell anymore, and the water follows sodium. That will lead to cellular swelling, which is the earliest change that we see with hypoxia. And as a result of that, all the organelles inside the cell, they're also going to swell up. So we want to have rough and plasma reticulum swelling, and that will lead to detachment of the ribosome, and that can lead to decreased protein synthesis. We want to have plasma membrane bleeding and a nuclear swelling, which can lead to chromatin clumping, right? So those are the reversible changes. I'll say that the irreversible changes is when the calcium ATPase is affected and the calcium cannot leave the cell anymore. So that will lead to increased intracellular calcium, and elevated calcium inside the cell can activate enzymes, right? Example like phospholipase, which is going to break down the cell membrane lysosome. So that can lead to cell membrane permeability, lysosomal rupture, right? And that can lead to release of hydrolytic enzyme into the cytoplasm, and that can lead to autolysis, right? And we also mentioned that excess calcium can also activate endonucleases, and that can lead to nuclear degradation. And then lastly, mitochondrial permeability. So the cytochrome C will enter the cytosol, and that will activate caspases, and that will lead to apoptosis and also decrease ATP production due to loss of proton gradients, right? All these efforts, in the next video, we're going to be talking about apoptosis. And then, like I mentioned earlier, if you are yet to subscribe to this channel, please don't forget to subscribe and then put on the notification bell so that each time we upload video, you're going to get the notification. Thank you.